Dear students, in the last class, we have studied about the molecular orbital theory, that is the part 1, which shows when two atomic orbitals they combine, it results the two molecular orbitals known as bonding molecular orbital and anti-bonding molecular orbital. Bonding molecular orbital results by the additive combination and anti-bonding molecular orbitals results by the subtractive combination of the wave functions. Now let us be study about types of molecular orbitals. There are three types of molecular orbitals represented as sigma molecular orbital, pi molecular orbital, and delta molecular orbitals. Sigma molecular orbitals are formed by the combination of SS, SP, or PP orbitals overlapping along the axis. Pi molecular orbitals are formed by the combination and overlapping of the p orbitals laterally. Delta molecular orbital is formed by the overlap or combination of the dx square minus y square orbital of one atom with dx square minus y square orbital of another atom when Z is the internuclear axis. Generally, p and d orbitals or only d orbitals of the two atoms form delta bond. Coming to the energy level sequence for molecular orbitals. As we know, the energy level sequence for the atomic orbitals, like electron in an atom, electron first it goes to 1s orbital, next goes to 2s orbital, next goes to 2p orbital, and so on. Now similarly, in the molecular orbital, when 1s combines with another 1s, it results sigma 1s molecular orbital and then sigma star 1s molecular orbital. Similarly, when 2s atomic orbital combines with another 2s atomic orbital, it results sigma 2s molecular orbital and sigma star 2s anti-bonding molecular orbital. Here, among the three p orbitals, px, py, and pz, we take into the consideration, as per the new notations, 2pz orbital overlaps with another 2pz orbital axially, resulting sigma molecular orbitals. These sigma molecular orbitals are represented as sigma 2pz and sigma star 2pz. The resulting px and py atomic orbitals, they overlap laterally to form pi 2px and pi 2py bonding molecular orbitals and pi star 2px and pi star 2py anti-bonding molecular orbitals. For the atoms or the molecules having the number of electrons 14 or less than 14, then the molecular electronic configuration will be as shown below. That is, sigma 1s molecular orbital is having lower energy and the increasing energies of this is sigma star 1s, sigma 2s, sigma star 2s, pi 2px is equal to pi 2py, which is smaller than sigma 2pz, which is once again the smaller than pi star 2px, is equal to pi star 2py and then sigma star 2pz molecular orbitals. For the molecules whose total number of electrons is 16 or greater than 16, then the electronic configuration of the molecular orbitals is slightly changed. There, the sigma 2pz molecular orbital is having lower energy than pi 2px and pi 2py bonding molecular orbitals. The increasing level is sigma 1s is less than sigma star 1s which is further lesser than sigma 2s, the smaller than sigma star 2s which is smaller than sigma 2pz which is smaller than pi 2px is equal to pi 2py which is further smaller than pi star 2px is equal to pi star 2py which is further smaller than the sigma star 2pz molecular orbitals. Now let us study electronic configuration of molecules. The distribution of electrons among the atomic orbitals is called electronic configuration of elements. Aufbau principle, Pauli's exclusion principle and Hund's rule are applicable while writing electronic configuration of atoms. Similarly, the distribution of electrons among the molecular orbitals is also called electronic configuration of the molecule. The above rules of electronic configuration are also applicable for writing electronic configuration of molecules. Now coming to the another term, that is bond order. It is defined as half of the difference between the number of electrons in the bonding molecular orbitals and the number of electrons in the anti-bonding molecular orbitals. Mathematically, it is given as bond order is equal to number of bonding electrons minus number of anti-bonding electrons divided by 2. Coming to the significance of this bond order. Bond order is equal to the number of covalent bonds holding the atoms in the molecule. Example, in case of hydrogen molecule, so between the two hydrogen atoms, only one bond is there. Hence, the bond order in hydrogen molecule is 1. Similarly, consider oxygen molecule wherein two bonds are present between the two. Hence, the bond order in oxygen molecule is 2. Bond order helps in predicting the stability of the molecule. Higher the bond order, higher the stability of the molecule. For example, bond order of O2 is 2 and bond order of O2 plus ion, molecular ion, is 2.5. This shows that oxygen molecular ion is more stable than oxygen molecule. Bond order decides the bond dissociation energy. Higher the bond order of a molecule, higher the number of electron pairs holding the atoms in a molecule. So, the bond order is stronger and more energy is required to dissociate the bond. Hence, higher the bond order, higher the bond dissociation energy. Bond order decides the bond length. Higher the bond order, lower the bond length. Example, bond order of molecular oxygen ion is 2.5 and molecular oxygen ion of double plus is 3. The bond length of O2 double plus is less than the bond length of O2 plus. Coming to the other terms, if number of bonding electrons is greater than the number of anti-bonding electrons, then the bond order will be high and the molecular stability will be high. If the number of bonding electrons is equal to the number of anti-bonding electrons, the bond order is 0, the molecule is unstable and does not exist. For a molecule to exist and to remain stable, number of bonding electrons must be greater than the number of anti-bonding electrons. Coming to the another term, that is a magnetic behavior. If all the electrons in a molecule are paired, then it is diamagnetic. The diamagnetic means it is not attracted by the magnetic field. If there are one or more unpaired electrons in a molecule, then it is paramagnetic. That is, this type of a molecule is slightly attracted by the magnetic field. The magnetic moment in a paramagnetic substance containing n number of unpaired electron is calculated by the equation mu is equal to square root of n into bracket n plus 2, where n is the number of unpaired electrons. The magnetic moment is expressed in terms of Bohr magneton. Keeping all these things in mind, let us study the molecular orbital configurations of homonuclear diatomic species. The first one, hydrogen molecule. Atomic number of hydrogen is 1. The total electrons in hydrogen molecule is 2. Its molecular electronic configuration becomes sigma 1s2. Bond order becomes 2 minus 0 divided by 2 becomes 1. That shows that there is a single bond between the two hydrogen atoms. So, since there is no unpaired electrons, so hydrogen molecule is diamagnetic. Let us consider hydrogen molecular ion, which is formed by the combination of hydrogen atom and hydrogen ion. In this case, the total electrons will be 1 plus 0 is equal to 1, and molecular electronic configuration will be sigma 1s1. The bond order becomes half, and this shows that there is a one unpaired electron, so hydrogen molecular ion is paramagnetic. So here I have shown the structure of hydrogen molecule. Now this is the molecular orbital structure of helium molecule. In helium molecule, so each helium atom contains 2 electrons. Therefore, total electrons in helium is 4. Out of the 4, 2 electrons in bonding molecular orbital and 2 electrons in anti-bonding molecular orbital resides. Hence, the molecular electronic configuration becomes sigma 1s2, sigma star 1s2. The bond order becomes 2 minus 2 divided by 2 will be 0. Hence, helium molecule does not exist. Coming to the helium molecular ion He2+. Atomic number of helium is 2, and this helium molecular ion is formed by the combination of He and He+. He contains 2 electrons, He plus contains 1 electron, so total electrons will be 3. Molecular electronic configuration is sigma 1s2, sigma star 1s1. Bond order becomes half, and one unpaired electron is there in the molecule. Therefore, this molecular ion exist in nature and it is paramagnetic. Coming to the lithium molecule. Atomic number of lithium is 3. Electronic configuration becomes 1s2, 2s1. Since 1s orbital of both the atoms are deeply seated, the molecular orbitals formed by the combination of these orbitals are considered to be non-bonding. Thus, we are left only with the 2s orbital in the valence shell. So, in the valence shell of lithium, we have only one electron. So, in the molecule, totally we have 2 electrons. These 2 electrons are in bonding molecular orbital of sigma 2s. So, the bond order will be once again 2 minus 0 divided by 2 will be 1. So, this molecule is not having any unpaired electron, therefore it is diamagnetic in nature. Similarly, the beryllium molecule also have the 4 electrons in the 2s orbital. So, the bond order will be 0 and this molecule also does not exist. Next comes the boron molecule. When I take the boron atomic number 5, electronic configuration 1s2, 2s2 and 2p1. So, this contains totally the 3 electrons, 2 in 2s and 1 in 2p, and total number of electrons in boron molecule will be 6 in the valence shell. So, therefore, molecular orbital electronic configuration becomes sigma 2s2, sigma star 2s2, pi 2px1 equal to pi star 2py1. So, the bond order becomes 4 minus 2 divided by 2 will be 1. This shows that there is a single bond between the 2 boron atoms. This has been verified by experiments. Due to the presence of 2 unpaired electrons, boron molecule is paramagnetic in nature. Coming to the carbon molecule. Atomic number of carbon is 6. Electronic configuration becomes 1s2, 2s2, 2p2. The total available valence electrons is equal to 8. Molecular electronic configurations will be sigma 2s2, sigma star 2s2, pi 2px2 is equal to pi 2py2. So, the bond order will become 6 minus 2 divided by 2 will be 2. That shows that between the 2 carbon atoms, we have the 2 bonds. Out of the 2 bond, one is sigma, another one is the pi bond. Since there is no unpaired electrons here, so the molecule is diamagnetic in nature. In a similar way, we can also explain the structure of the nitrogen molecule. So, the total number of electrons in the valence shell will be 10 and molecular electronic configuration sigma 2s2, sigma star 2s2, pi 2px2 is equal to pi 2py2, sigma 2pz2. The bond order will be 3 here. So, the nitrogen molecule is formed by 1 sigma and 2 pi bonds. The molecule is diamagnetic in nature. Similarly, we take the oxygen molecule. When we come into the oxygen molecule, in the 2p, there is a slight change in the energy levels. Here, 2p z orbital is having lower energy than the pi 2px and 2py orbitals. This is because of the atomic number is 16 and above. Now, the atomic number of oxygen is 8. Electronic configuration will be 1s2, 2s2, 2p4. The total valence electrons will be 6 plus 6 is equal to 12. Molecular electronic configuration is sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2 is equal to pi 2py2, sigma star 2px1 is equal to pi star 2py1. The bond order will be 8 minus 4 divided by 2 will be 2. In oxygen molecule, there is a double bond between the two oxygen atoms, out of which one is sigma, another one is pi bond. The bond length is 1.21 angstrom and bond dissociation energy is 493.7 kilojoules per mole. The molecule contains two unpaired electrons, hence oxygen molecule is paramagnetic in nature. The paramagnetic behavior of oxygen is only explained by molecular orbital theory. This is the success of molecular orbital theory. Now coming to the oxygen molecular ion, which is O2 plus. This is formed by the combination of oxygen atom and oxygen cation O plus. The total number of electrons will be 6 plus 5 is equal to 11. So the molecular electronic configuration will be sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2 is equal to pi 2py2, pi star 2px1. This shows that the bond order here is 2.5. It is also paramagnetic in nature and its bond strength is greater than oxygen molecule because of the increase in the bond order. Similarly, we take oxygen molecular ion O2 minus. So this O2 minus is formed by the combination of oxygen atom and oxygen ion in a negative state. Here the total number of electrons will be 6 plus 7 is equal to 13 and the molecular electronic configuration becomes sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2 is equal to pi 2py2, that's pi star 2px2 is equal to pi star 2py1. So the bond order here it becomes 8 minus 5 divided by 2, that is equal to 1.5. Oxygen molecular ion, that is O2 minus, is paramagnetic in nature and its bond strength is less than oxygen molecule. Coming to the next fluorine molecule, whose atomic number is 9. Total number of valence electrons will be 14 and the molecular electronic configuration you must able to draw. And the bond order becomes 1 and between the two fluorine atoms you have one sigma bond. Since there are no unpaired electron, fluorine molecule is diamagnetic in nature. In the similar manner, neon molecule, the total number of valence electrons is 16 and the bond order becomes 0, saying that there is no existence of neon molecule. These are all the explanations regarding molecular orbital configurations of homonuclear diatomic species. Now coming to the explanations regarding heteronuclear diatomic species. Heteronuclear diatomic species have two different atoms linked together. These are AB type species in which B has higher electronegativity than A and both the atoms A and B have 2s and 2p atomic orbitals. That is, A and B are p block elements of second period of the periodic table. The diatomic molecules having less than or equal to 16 electrons in all show sp mixing. Example: nitrogen, carbon monoxide, the carbon molecule, boron molecule, Bn, etc. So this is the molecular orbital diagram for carbon molecule. It contains the total electrons will be, so the valence shell, so it is 10 electrons. So 2, 4, 6, 8, 10 and 12, sorry, it contains the 12 electrons, total electrons in carbon. But the valence electrons, if I remove the one s, it contains only the totally the 8 electrons. So this is the molecular orbital diagram for the carbon molecule, and this is the molecular orbital diagram for the nitrogen molecule. Students, you must able to draw these structures. Now this is the molecular orbital diagram for oxygen molecule, which shows the two unpaired electron. So the oxygen molecule is paramagnetic in nature, and here the sigma 2p z orbital, molecular orbital, is having lower energy than the pi 2px and pi 2py molecular orbitals, whereas lesser than the oxygen, so we have lesser than the oxygen, we have the sigma 2p z molecular orbital is having higher energy than pi 2px and pi 2py molecular orbitals. So this is the molecular orbital diagram for the fluorine molecule, and also this is the molecular orbital diagram for neon molecule. Now let us take the molecular orbital diagram for, we were discussing about heteronuclear molecules. In heteronuclear molecules, the energy difference between 2s and 2p orbital is quite less, and due to it, the 2s and 2p z orbitals tend to overlap and also to mix. Due to this, energy of 2pz increases and it is placed above the pi 2px and pi 2py in the molecular orbital diagram. However, in diatomic molecules having more than 16 electrons, due to the absence of overlapping of 2s and 2pz orbitals, sigma 2pz orbital is having less energy than pi 2px and pi 2py molecular orbitals. Example, oxygen, fluorine, and so on. Coming to the molecular orbital structure of carbon monoxide. Here oxygen is more electronegative than the carbon, so therefore the oxygen energy levels are lower, carbon energy levels are higher. Atomic number of carbon is 6 and oxygen is 8, and total valence electrons in carbon monoxide is 4 plus 6 is equal to 10. Molecular electronic configuration of carbon monoxide is sigma 2s2, sigma star 2s2, pi 2px2 is equal to pi 2py2, then sigma 2pz2. The bond order becomes the 3. This shows that carbon and oxygen atoms in carbon monoxide molecule are linked together by 1 sigma and 2 pi bonds. The structure is shown as a C triple bond O, where carbon is also having one lone pair of electron, oxygen is also having one lone pair of electron, and each carbon and oxygen attains octet structure. Both the carbon and oxygen atom attains octet configuration. The molecule has no unpaired electron, hence it is diamagnetic in nature. Coming to the another molecule, that is nitric oxide. Atomic number of nitrogen is 7 and oxygen is 7. So the total valence electrons in nitric oxide is 5 plus 6 is equal to 11 electrons, and molecular electronic configuration of nitric oxide is sigma 2s2, sigma star 2s2, pi 2px2 is equal to pi 2py2, sigma 2pz2, and pi star 2px1. The bond order becomes 8 minus 3 divided by 2 will be 2.5. This shows that nitric oxide molecule is having 2 electrons bond and one is having 2 electron bond and one 3 electron bond. The structure is shown. So in this structure, the nitrogen is having a lone pair, oxygen is also having a lone pair, and the double bond. There is a one bond between nitrogen and oxygen, wherein the 2 electrons of oxygen and 1 electron of nitrogen combines to form 3 electron bond. The presence of one unpaired electron makes nitric oxide paramagnetic. The bond dissociation energy of nitric oxide molecule 667.8 kilojoules per mole, which is less than that of the nitrogen molecule, that is 945.6 kilojoules per mole. This is because in nitric oxide bond order is 2.5 and in nitrogen the bond order is 3. Coming to the another nitrosyl ion, that is NO+. In NO+, the total number of electrons of N and O+ will be 5 plus 5 is equal to the 10 electrons. So the molecular electronic configuration will be sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2 is equal to pi 2py2. The bond order becomes 8 minus 2 divided by 2 is equal to 3. This ion is having 1 sigma and 2 pi bonds. The structure of the nitric oxide is shown. Between the nitrogen and oxygen we have the 3 bonds, and each nitrogen and oxygen is having the 1 lone pairs of electrons. Since the ion has no unpaired electron, it has diamagnetic character. So this is the molecular orbital diagram for carbon monoxide. Students, you must able to draw these structures. Of course, here it is showing how S and 2s and 2pz orbitals are mixing, resulting the molecular orbitals in carbon monoxide. This is the molecular orbital diagram for nitric oxide molecule. Of course, this is another diagram for the nitric oxide molecule. This is the molecular orbital diagram for nitrosyl ion. This slide shows the comparison between molecular orbital theory and valence bond theory. Valence bond theory says separate atoms are brought together to form molecules. Molecular orbitals are formed by the overlap and interaction of atomic orbitals. The electrons in the molecule are paired to accumulate density in the internuclear region. The accumulated electron density holds the molecules together. Electrons are localized between two specific bonds. So like this, the valence bond theory and molecular orbital theory comparison is given in this slide. This is also the slide that shows the comparison of valence bond theory and molecular orbital theory. Students, goes through this comparison and try to note down. This is a slide that shows the difference between atomic orbitals and molecular orbitals. Atomic orbital is the region having the highest probability of finding an electron in an atom. Molecular orbital is the region having highest probability of finding an electron in a molecule. Like this, there are many comparisons are given in this slide. Please go through this. This is the another slide that shows the comparison of valence bond theory versus molecular orbital theory. Students, go through these aspects and try to learn. Thank you.